So now we've seen how limits can work for multivariable functions. So now we're going to do with limits what we've done previously, but for single variable for functions y equals f of x. So previously we saw that we could define the derivative using limits. So here we go, dy dx equals limit as h goes to 0, fx plus h minus f of x over h. There's different ways to write this down. Here's one way to do it. So now let's write down the limit definition for the derivative of fxy. Now, first of all, of course, we have to say which derivative we're going to do. And again, we're going to start here with the same derivative we start with in class, which is to say the partial derivatives. So now, how do you make a partial derivative? So let's say we're talking about df dx. What does that mean? This is the derivative that happens as x is changing, but y is constant. So how can we write down the limit definition? Oops, that went too far. Okay, how can we write down the limit definition, knowing that we want to write down some that looks like this limit definition, but we also want to have it as a function of two variables where x is changing and y is constant. So that's going to put all those things that we need to do, put them all together, and we get for z equals f of xy, the partial derivative df dx equals limit as h goes to 0, f of x plus h comma y minus f of xy over h. So notice that this looks quite a lot like the y equals f of x derivative, but we've got y staying constant, and x is the one that's varying, so x is the variable that gets the plus h. And then, if we want to write down the limit definition for df dy, we get a very similar thing. Now in this case, x is the one that's constant, and y is the one that's varying, so y gets the plus h. Okay. Now, so the first sort of derivative that we talked about was this. Now we also talked about multivariable functions using vectors. So what I'm going to do right now is I'm going to turn this into vector notation. And then we're going to do something with that subsequently. So let's take a look. So let's rewrite this using vector notation. So remember that we can think of xy not just as a point, but as like a position vector. And then that's the varying part. And then the sort of h gives us is like a, let's see, if we can break off that part is what I should say. So we can rewrite x plus h comma y as the vector xy plus the vector h0. Okay. So next, we're gonna write this out using more vector notation. So for position vector x comma y, our notation for that was r. That's the r vector. And now we also have that the sort of direction vector for the x direction is I. That's the vector 1, that's the unit vector in the x direction 1 comma 0. So we can rewrite the vector h0 as the vector in the x direction of magnitude h, which is the value h times I. And x comma y is just r. So it looks like this. So what does this mean? So geometrically, what does it mean to let h go to 0? So we're at some point, some position, r equals xy. And from there, we want to move in the direction indicated by the unit vector I, but we're going to head in that direction a smaller and smaller magnitude, as indicated by h. So here is the limit definition for the derivative, partial derivative df dx, but written in vector notation. But now that we've put this in vector notation, we can remember, next the thing we can do is we can remember that partial derivatives are not the only sorts of derivatives that we've talked about. The other derivatives that we've talked about, not just derivative in the x direction, not just derivative in the y direction, but the derivative in any direction, as indicated by a vector. So now that we've put this in vector form, we can now apply this using any vector. So this gives us a way to define directional derivative with limits. So let's say that we have a unit vector r comma s. Then we can just say the derivative in the u direction, d sub u of f, is the limit as h goes to 0 of f of r plus hu instead of hi minus f of r over h. And that's writing the directional derivative in vector notation as a limit. But now we can also unpack it and put it back in xy coordinate notation. Let's take a look. So we can unpack r as just the vector xy, u as the vector r comma s, and that gives this. And then finally, we can write these straight up as coordinates. So the limit definition for the directional derivative of f in the direction of u is limit as h goes to 0 of f of x plus hr, comma, y plus hs, minus f of xy over h. And I'll just mention that in this case, we wanted u, the vector u, as always, we want to indicate direction, but no magnitude. Pure direction means it has to be a unit vector. What if we used a vector that was not a unit vector? We'd have to divide by the magnitude. Okay. So now let's take a look at how to actually set this up. Okay. So here's a function, f of xy equals 2xy over x plus y squared. So let's write down the limit definition for this particular function of df dx at the point a comma b. So what does that look like? We want the limit as h goes to 0, f of, so we're at the point a comma b, so we're not going to use x and y. So it's going to be a plus h comma b minus f of ab all over h. There's the sort of general, that's the definition, but now we have to apply it to this particular function. So we get, so f of a plus h looks like what? 2a plus h b minus 2ab over h. Limit as h goes to 0. Oh, sorry, I forgot the fraction. Sorry, let me back it up. Okay. Over a plus h plus b squared for the first one, and then over a plus b squared. Sorry, there's the whole function. All of that over h. So that would be the limit definition of the derivative df dx for this particular function. We're not going to calculate this. We're not going to simplify it. We're just writing down the limit definition. That's as far as we are going to go. Next, directional derivative. What does that look like? The limit as h goes to 0, f of, and we're at the point AB, so it's a plus RH, comma B plus SH minus f of AB all over H. That's the general limit definition, and now we've got to plug it in first of all for this function, and second of all, we know that the U vector is 0.6, 0.8, and that's a unit vector. So Q A plus 0.6 H, and then B plus 0.8 H over X, so A plus 0.6 H plus Y squared, so B plus 0.8 H squared. Okay. Minus, as always, 2AB over A plus B squared, all of that over H. Again, this is just the limit definition of what the directional derivative would be. We've written it down. That's as far as we're going to go.